began on molecular symmetry to order parameters.
Thanks, Chair. So it is a great pleasure for me to give talk here. Today I was talking about from molecular symmetry to the order parameters. I think everybody knows what's the molecular symmetry, but what's the order parameters? The order parameters is used to describe the symmetry breaking of macroscopic phase. So I try to understand what's the relation of molecular symmetry and the macroscopic symmetry. So first of all, I will give the brief introduction about the phenomena and the classical models. So actually, for the rigid rod, this is the polymolecular. 5CB maybe is not a good example. For example, another is biomolecular. So the symmetry is different. So actually, for rod, you have the pneumatic phase, somatic A phase, somatic C phase. For the disc, the symmetry is same as the rod, but the phase, the somatic phase is different. It means the symmetry is not enough to describe the phase. So then the shape is also important. For the polar molecular, they have the S star, SA star, a lot of blue phase. For the bundle molecular, now there are also a lot of phase, but it's not clearly. So defects is also very important. So like the point defects, discrimination length, what's the inducement? Most of the case is boundary condition, geometric restriction. For example, like we have mathematically, we have the Hereford theorem. It means this low non-relation continuous tangential vector field and the even dimensional n spheres. So that means defects exist. So another is dynamics. So I also ask myself question: can defect be a stable or metastable state? Didn't have these three cases. It's just in the bulk. This is possible? I don't know. So actually, there are a lot of the models. Actually, most of the model is for the pneumatic phase, but just a few models is for the somatic phase. Like the analog model, Maysap model, McManning model, and a lot of people also talking about the lambda DG model. Like the vector model is the Ocean-Frank model, X model, Chernobynsky model. A lot of models about that. What's the relation of the models? For the polymolecular, just few models, but most model is formological. For the bundle model, it's not clearly. I think most of the time is a formological model. Even the other parameters is a problem for mathematicians. So I try to answer the question. First of all, what's the representation for the config space of the molecular? So how to choose the other parameters? What's the relation the molecular model? The molecular model here, because I'm talking about the mean field theory, the molecular model use the probability density function. What's the tensor model? It means like the anti-G model. We say this is the tensor model. We say, what's the relation to the vector model? Vector model, like the Ocean-Frank model, we say this is the vector model. So what time the pneumatic phase is stable? If we understand the pneumatic stable, maybe we can understand what's the somatic phase. So because when the pneumatic phase low stability, that time maybe go to the somatic phase. So first part, I was talking about what's the molecular symmetry, go to all the parameters. So because now we can consider the rigid molecular. So mathematically, this is body fixed oxygen frame is 6. 3 of them is the space, 3 of them is the frame. It's like the frame. X, Y, Z, maybe you say M1, M2, M3. So reference frame, we say this one. because they can be changed. So this is for the rigid body, for any rigid body. So the determination of the config space, this is a translational invariant. So let's say P is SO3, so then M1, M2, M3 could be expressed in this way. So description of fixed point and molecular coordinates in the body frame in the position in space, you can be used as this way. So now I'm talking about the density functional theory. I say this is the mean field theory. Use the virial expansion, but this is valid only when the C is small, because I just keep the two molecular interaction and throw away three molecular and more molecular interaction. So that time the free energy could be rested in this way. This is the entropy. This is the two molecular interaction. So under this constraint, this means the density, average density is a constant. So here, important thing is the pair interaction. This time you use the Mayer function, like use this way. So we say this is pairwise interaction. But this formula is just when C is small, but for high density functional, that case, the Callahan-Stirling theory is good, but this is formological. This is this is a very good theory, but today I didn't talk about that one. So actually, this model is a starting point for me. Actually, I'm a mathematician. I always need a starting point. If you think the starting point is not right, I didn't know how to do that. So important thing is the pairwise interaction. So actually, we use we model the rigid molecule with the spheres with the radius R0 distributed in space with probability density functional. So it means the pair interaction uses this way. So the potential have the two cases. One case we use the hardcore potential. That time is just exclude volume. Actually, Isaac uses this formula for the hardcore potential. This is good for the light traffic Lie crystal because here you didn't have include of the temperature. If you use the potential, use the non-juice potential. That time it means you have the repulsion and attraction. So this means this model could be for the light traffic and the semi-traffic Lie crystal. Important thing is for the hardcore, some of the analytics we can deal some analytically. So, but if you use the non-juice, this is good, but this is difficult to analysis. So this is actually you have the two things. One thing you use the atom like the discrete case, Actually, a lot of the Monte Carlo simulation use this way. Another way, you use the molecular act this way. It means use here is the integral. It means the molecular is like the rod. Is actually the rod. Is here. For the bond Q, you use this way. Actually, this formula could be used any shape of the molecule. But a different shape, the dimensional is different. So now, first of all, talking about the kernel function properties, because this is important in the formula. So we have the proposition because two molecular change it should be the same. And the translation invariant. And if for any t is the SO3, this should be right. Then we can define the homogeneous kernel function. Actually, Isaac did that way, but just for the molecule, for the rod. So then Gp and P prime is invariant in X. That is well defined. So it means you just suppose this is a spatially homogeneous phase, like the lemmatic phase. So then we can use the homogeneous kernel like this way. So this is exactly what Isaac did. So we have the position because the G have this property. Actually, this is exactly of the representation of config space. We can use, for example, you can use the FP, P is the SO3. Sometimes you can use the M1, M2, because M1, M2, M3 is the M1 times M2. Or sometimes you use the quaternion. But which is bait? Which is bait? One thing is the probability. Another way is the G. You have the include of the interaction of the two molecules. So how to get the parameters? Parameters, first of all, you have the molecular symmetries. The symmetry, from the molecular symmetry, you can get the symmetries of the kernel function. You can get the symmetries of the probability density function. Then we can try to choose of the other parameters. But even in this case, we have the infinite other parameters. So this is not enough. So now we have the symmetry of the kernel function. We try to simplify form of the kernel function. But this is with intuition from the experimental stimulation and the good approximation of kernel function. Most cases, we take the leading old, like the method, like the Professor Wax taking just the second old. So this is, but sometimes maybe the second order is not enough. We didn't know. So then use this way we can reduction of the other parameters. Another important thing we say is the molecular parameters. What's the molecular parameters? Actually, for the molecular parameter, two of them is we say is the control parameter. One is the average density. Another is the temperature. This is could be experimentally could be controlled. Another important thing we say is the molecular shape. Molecular shape, they also get some of the parameters. Like for the rod, we have the length L, and the diameter of the rod is the D. We say this is molecular shape, the parameters. So the molecular parameters is goes for the coefficients in the approximate the kernel function. So then the field reduction of the other parameters. I will show you later. So now talking about the process of homogeneous kernel function, the molecular symmetry leads to symmetry of the G, the peg function. You have the same. If molecular is the symmetry under the T, then we have this property. So we have refraction symmetry about the plane with the normal vector, we have this property. If, for example, like the molecule just in the plane, so that case, the G could be written in this way. Pij is the mi dot the mij prime. So now we have the corollary. For the Banker molecular, G depends on the P11, P12, P21, P22. So you have this polity. For the polar rods, G depends only on the P11. This is the function. For the non-polar rods, G depends only on the P11 absolute. So these properties is for the hardcore is also for the Lerner-Jones kernel. It's not dependent on the formula. This is just the symmetry reduction. For that, what are the other parameters? Other parameters most of them use the moment of the PDF. In the moment, we have the Lagrangian equation. So if the molecule is symmetry and of T, F should have this property. For the rod-like molecular, the other parameters of M1 vanish. For the Banker molecular, moments with M2 and M3 occurring the all times vanish. So now approximate G by polynomial of Pij. A term leads to the production of two moments in the energy functional. So by the Euler Lagrangian equation, f is fully determined by the three moments. They literally become the order parameters. Where to truncate it is decided by the results of experimentally and the numerical simulation. For example, for the Rolex, maybe just take the leading odd, like the mess up. But for the bond core, maybe third odd is not enough. Maybe we need the third odd, I don't know. So now, the symmetry G decided on large terms. For the raw molecular, for example, you just take leading odd, it is the P11 square. For the polar rods, because now you have the P11, first order. For the bond Q, if we take the blue of the second order, you have the four terms. If we keep of the third order, another four terms come in. But maybe truncate here is good, maybe not. I don't know. So this is dependent on the numerical simulation or experimentally. So the coefficients of these terms rely on the temperature and the molecular parameters. They also affect the choice of the order parameters. I will talk in later. So for the rho-like molecular, my soft potential is like this way. P11 it means M1 dot M prime. So F is extra symmetry. It means this average we have the this way. So here you have the two parameters. One is S, one is B. But the only other parameter is S. This is consistent with experimentally. Your axonomatic is the only homogeneous phase found under the isotropic phase. If you say this is only one parameter, we have to prove B is the 0. B is the 0. So now the three groups prove that B is equal to 0 for the mass-up potential. It means that case for your like molecular, you truncate, you suppose the mass-up is good, then only one parameter. So this is dependent on the formula. For example, if you use the Anzag, it is difficult to prove only one parameter is enough. So far, maybe it's right. So far, mathematically, we cannot do that. So for the polar rods, now for the polar rods, they have two terms. So now you have assumed for the M1 pass to one of the eigenvalue. If C1 is less than 1, M1 is 0. So it means M1 you have this formula, and M1, the K is one of the N or N prime or the third one. So mathematically, you can prove that just three order parameters, SB and S1, for the polar rods. But the micro-reduce indicate stable phase gives the uniaxial. This means B is equal to 0. It means just 2. But mathematically, this is difficult to prove that. So this is for the polar rod. For the biomolecular, for example, like you just keep the similar to the mass up, just keep up the four terms. So you can also prove M1 equal to 0. If C is small, M11 and M22, because in the bond Q you have to use of the M1, MF2, because one direction is not enough. So could be diagonal simultaneity. It means M1 pass to one of the eigenvalue. So that case we have the five parameters. Maybe some of them is 0. It could be reduced, but so far I cannot prove that. Physically may say just the 2 from here is important. Maybe three of them is important here, because in this case includes the biaxial case. Of course, the Lubinsky have a paper say maybe the third order is not enough. You need the two order moments is not enough. You need the third order moment. So this is another case. So before I talk about it, now I try to understand the molecular model, how to reduce the tensor model, how to reduce the vector model. Then we can understand the different level model, what's the relation. So we say that if you use the A PDF, we say this is the molecular interaction, we have the molecular model. If we use what's the tensor model? You will use the closure. I like the Bingham, I will express to you. Use the tiny expansion. Then this type of model could be reduced of the tensor model. We can get the nano-Degen-like model. If this type of model restricts to symmetry, it means Q right in this way, then you can get the vector model. So the other parameter is like the C, S, and A. But some cases you C is constant, S is constant, you get the ocean Frank. If C is constant, S and A is not constant, S is not constant, you get the X. So, so this is my research is the guide. So, first of all, actually I like the Bingham closure very well. What's the Bingham closure? Bingham closure is some sense the PDF restricts the Gaussian because this is Gaussian. But keep the second moment is not changed. Actually, it's not difficult to prove PQ and Q is a one-to-one map. It's a one-to-one map. So what's the Bingham closure? Bingham closure it means the F is Gaussian. Keep the second moment, not change it. This is Bingham. Actually, now we have the molecular theory in this way, right? In this way. So I use the hardcore because hardcore is easy to analytic. So this one is derived for Lagrange potential too, but it's difficult to analysis. So now you use the tiny expansion. Tiny expansion, it means this molecule is not far away another molecule. So use the tiny expansion. So then you can reduce of the F in this way. Actually, Anzager is getting this formula. But if you keep more terms, you can get the elastic energy. So Bingham closure, it means that you use the Bingham closure truncation, then you can get the tensor models. So for the hardcore potential, everything could be calculated exactly. So I will show you. For regular rods with length L and length D, both edges are the half spheres. This is a little bit different in the original Anzager paper. So for the two rods with interaction M and M pi, the interaction region is composed of three parts. One part we say the body-to-body part. Body-to-body part is like this region. Another is body-end part. Is end part. Actually, because for the hardcore, the pi interaction is a corrective function. It means the function is equal to 0 or 1. So only the region is the important. Here is the region. So now you have the region where you can get the volume of the interaction region. Is this one. Exactly, you can get this formula. This is Anzager. This is Anzager. Anzager get this one. He say the D and L is very small. It means the molecule is very long. So this term and that term is throw away. just keep this term. This is unlike. So this is unlike. It means leading out in this way. This is, we can get the unlike model. So what's the main sub model? Main sub model could be getting in this way too, but this is different. If the kernel function is based on the Lennard-Jones potential, so in the sense of the leading out, actually, you can, this function is not clearly just depend of the molecular parameter under the temperature, but this is a function of cosine gamma. So, main sub means just take the leading out. This is constant. Is not important for the lemmatic phase. But the next order is this term. This term exactly is the main sub potential. Actually, main sub is just considered attraction. They didn't have the repulsion. Here we have also repulsion. But from this way, mathematically, we can say what's the main sub. So now, let's go wrong. To the second moment. Return to the hardcore. First moment, you can prove that this is 0, because this is symmetry. This is 0. But this is not 0. For the second moment, this is a matrix. This is not 0. Actually, we can prove this matrix could be read in this way. For example, let's see what's the N1, what's the N2. Let's see what's that one. N1 is here, N2, N3, N2, N2, N3. So then we can get A1, A2, A3. So where the A1, N2, A3 is the meaning. So you can get the exactly like the unlike did. You can get the A1, A2, and A3. But A1, A2, A3 is not a good formula. So you have to change it out this way. Change it to the M. But now you change the M, you can get also B1, B2, B3. B1, B2, B3, but now sin gamma is here. It's bad. But these two terms is like this way. This is a good term. But you separately you see this is a bad term. Actually, this is like big potential. Now we project into the also polynomial expansion. This is like the main sub did. So now we drift the high term, drift away the high term. For the fourth order, it's much complicated. We can do it also. So now we use the true tensor. This is true tensor. Actually, because I use the Bingham closure, it means the fourth tensor is a function of the Q tensor. So then we get the Q tensor model. Actually, from here to there is the energy. For the lemmatic phase is enough. Some case maybe just goes away this way, this way. Actually, like the Zhang's paper is exactly similar here. C is constant and no other terms. So because the Bingham closure could be guaranteed the Q, the eigenvalue of Q is larger than minus 1/3. Now we can also get the elastic. Elastic just this is Q2 because Q4 is a function of Q2. This is Bingham closure told us. So sometimes we need the fourth order, the fourth order, the tensor. This is also we say is elastic. Because if you think about the nematic phase is low stability, so that time we need the next order. So here, the coefficient E1 to J1, EI, JI, NI only depend on the it. It is the order parameter. The parameter is only dependent on the it. And the BQZ Q4 is determined by the Q2 with the Bingham closure. So the model, some sense, is very simple. So this type of model is good for the electrotropic Lie crystal because you use the band core. You use the hard core potential. So only have the two-dimensional parameters, alpha and eta. This is same as the molecular model. So now I'm talking about the vector model. So let's suppose this is constant density. It means C is constant. Let's suppose this is your axial approximation. Then you can get the ocean flank. So get the ocean flank. Of course, you can also get the Q4. So K1, K2, and K3 is just the depend of the eta and S2 and S4 because S4 is a function of S2. So you can see that for the eta equal to 0, it means the rod is infinite length. So then we can see the K3 is large as K2 and large as K1. But when the length is changed 1 or 10, it means the 1 or 10 is the length. So it's the same thing. It's the same thing. But when the eta is 1/6, it means large, very long. So now the K1 and K2 is almost the same. Interesting thing, if the 1/5, K1 and K2 is the size is changed. So when eta is 1/4, that time the K1 sum is negative. It means in that case, the nematic phase lost stability. So for 1/3, is a big problem. So actually, there are a lot of the experimental to observe with the K1, K2, K3. So most of the case is the eta is the length is 1/4, larger than small 1/4. So from how the theory is predict, so in the same sense, if the rod is too short, maybe the nematic phase is lost in the stability. So actually, the procedure could be applied to different shape. Actually, I'm working on that. For example, like the polar band core, but it is much complicated because the interaction region is complicated. The procedure could do that. So now I'm talking about modeling for the somatic phase. So actually, we suppose Q2 is S2AA minus 3 1 over. It means uniaxial. And this is constant. This means S is constant. That time, just the two order parameters. One is the C, one is the S2. One is the C, one is the S2. Actually, we didn't know what's the periodic length. Theta it means the angle. So now I can get the one-dimensional model for the somatic phase. So from here to here is exactly we say this is the zero order term. This is the second from here. This is the first order. It means this model is similar with the Landau-Podolsky model. Then it means if you have the somatic phase it means we need the different derivative. But we have the two other parameters, C and S. The periodic is generated by the function. So the coefficient E1, ER, JR, AR depend on the eta and the theta. Being the S4 is determined by the S2 by Bingham closure. So this model we can get this. Okay, this model we can get the symmetric A phase, no problem. Because when we just see the second order term where low sum the K2 coefficient is the negative. That time we can get the symmetric phase. So I also talking some of the related works. Simulation actually for the symmetrical crystal, when the kernel function is based on the Lennard-Jones potential, we can use the molecular model studied of the symmetrical crystal in the homogeneous situation. Like, for example, you can get the boil temperature, you can get the phase diagonal, it means the temperature density, you can get the phase diagram. You also can use that for the phase separation. The approach is applicable for different shape molecular, but the difficulty is complete the molecular model in the calculation of high-dimensional integral, because this model is the dimensional is very high. For example, like for the rod-jet, and this is 8-dimensional problem for the disk. This is a 10-dimensional problem. For the bond Q-molecular, this is 10-dimensional molecular. So because my background is scientific computing, this is challenging, but I can do that. So get the phase diagram. Another is the analysis. Analysis, actually, I'm interested in the dynamics. Actually, for the molecular model, we call the Doi-Anderson model. Actually, Greg, he said this is the Doi-Hayes model. Some people say this is Doi-Smoluchowski model. Anyway, this is the same thing. I call this is Doi-Anderson model because that time the diffusion is just the translational diffusion on the rotational diffusion. Because for the Roger molecular, just two types of diffusion, translational and rotational. So I think this is you can find it in the Doi book. So you can use the Bingham closure and the Taylor expansion. You can get the tensor model. So from the tensor model to the vector model, this is the Erkin-Leslie model. A lot of people are talking about the Erkin-Leslie model. Here you cannot assume, like the free energy, we cannot assume isometry constraint as a steady state, because the isometry cannot keep in the dynamics. But we have to make the expansion near the equilibrium state. So you can also, from here to here, make expansion near the equilibrium state. So actually, this is all the direct model. The total energy, you can read it in this way. You can get the dynamic of the tensor model. So this tensor model is deduced from the molecular model. You can keep two kinds of diffusion. One is diffusional, translational diffusional, another is rotational diffusion. From this model, for the derived Erkin-Leslie model, actually, we can also from the Doi-Anderson model get the direct model. So for example, like the AF is make expansion in the equilibrium, and some the dipole number is small. This is like they say mathematically say this is a Hilbert expansion. So the formal derivation, the A and the V zero to this Erkin-Leslie equation. Actually, Hizou and Masatori did it in the 1983 for the homogeneous case. That case, you just get the Leslie. So in the 2006, we can get the Erickson because it includes our inhomogeneous interaction. So now you can prove this theory could be converged to this theory. It means we can control FR and VR. This is analysis. So I also work in the defects. So actually, you have the higher body theorem. This means there must be defects if the liquid crystals are confined on the spherical surface. So actually, a lot of paper under this way. So what I'm interested. First one is the model. You can use the molecular model, tensor model, and the self-consistent field theory model. Okay. So my question, actually they are split, tennis ball, cut and rotate, rectangle. My question, which is more stable? So actually, some size is the tennis ball is much more stable. Some size is split. So actually, this is my collaborator. So JF is the working his features. He worked in the Waterloo University. Wei Lang, he is working in the Princeton University and the Peking University. And Zhi Fei is my colleague. And a lot of students work with me. So thank you for your attention.
Thank you very much. We're pretty much on schedule, a little bit behind. Are there any quick questions?
Well, it's a comment actually. At the beginning, it seemed like there wasn't a clear distinction between polarity and chirality.
Chirality is a little bit different. So far, I just think about the shape, just the shape.
But the N star you were referring to, what is that?
I mean, if only the shape is different, maybe you can see the same thing as the A star.
So you don't mean chiral in that.
So far, I didn't include of the chiral.
For this model of smectics, I mean, you have all the numbers somehow, so does it give some kind of variation in the density of the right order of magnitude, and why was it restricted to one dimension?
Because now I suppose this is one dimensional.
Yeah,
Because I say the A is in the normal, or maybe in this way. Actually, the model could be three-dimensional. But now, because you think about just the symmetric phase, symmetric A and symmetric C, one dimensional is enough. So it's of course another problem is why one dimensional is the global minimum for the if you think about three-dimensional. But physically told us so they will choose one-dimensional structures.
But do people in the literature consider this kind of model rather than the one that, say, we had described earlier in the workshop? And does it give, I mean, can you represent these surfaces that Randy Camion was talking about as being the level sets of the density or something?
This is different. Actually, here we just suppose this is one-dimensional. Then you can get the one-dimensional structure.
Yeah, but in general,
If you consider this two-dimensional, maybe this one-dimensional solution is stable. Maybe not. So but now in that case, the model is much complicated.
I think we should move on. Thank you very much once again.